Good morning. We just have one more little thing I wanted to talk about while we're talking about the Earth and gravity and things like that. This doesn't have anything to do with gravity, but it's kind of falls into what we've been talking about with tides and other things. So I wanted to talk about why we have seasons on Earth. And the Earth, I'll put the Earth over here, spins on an axis. If the sun is over here, then light from the sun comes and hits the Earth, almost comes in almost parallel. The sun is far away. So if we have a point on Earth, let me pick a point over here. Some little chunk of the Earth right there. And the sunlight is coming in like this. It comes in at kind of an angle like that with respect to the surface. But 6 months later, the Earth has moved and it's on the other side of the sun. I'm going to move my sun. It's easier in my drawing here. So if this is now, and this is 6 months later. 6 months later, the sun is on the other side. So this same point on Earth is now over here, right? Same point on Earth. And what's the sunlight doing? It's coming in almost normal to the surface like that. So think about what happens if you take a flashlight and shine it at a piece of cardboard or something. If it's straight on, if it comes in normal to the surface, you get all the light concentrated in a nice small circle here. But if you tilt that paper, the light gets spread out over a big oval. The light gets spread out over a bigger area. So each little square centimeter of paper that the light's hitting is absorbing less light energy. Whereas when it's straight on, there's lots of light energy being absorbed by every little square centimeter of the paper because it's concentrated. The light's more concentrated. Well, the same thing happens to the Earth here. This would be our summertime. Because the light's more concentrated, where the surface of the Earth is heating up more, it's absorbing more of the sun's energy per square meter. This would be our winter time. The light is spread out and the Earth doesn't heat up as much. The Earth's surface doesn't heat up as much. And you can see why it's the exact opposite in the southern hemisphere. So this is interesting because somebody did a video. They took their video cameras to Harvard on graduation day and asked Harvard graduates why we have seasons on Earth. And the story is that in the very eloquent way that you would expect a Harvard graduate to describe something, they basically said that at certain times of the year, the Earth was closer to the sun than at other times of the year. Then they went to an elementary school and asked the little kids why we have seasons on Earth. And in the very cryptic way that you would expect elementary school students to describe something, they basically said that at certain times of the year, the Earth was closer to the sun than at other times of the year. So they both got it wrong. But that's kind of an example of a little bit of knowledge can be a dangerous thing. Because if you know that you step up to a campfire, it gets warmer, You step back, it gets cooler, right? You know that. We've done that probably, or you've held your hand close to the stove and it was hot and you pulled your hand away and it wasn't hot anymore, right? We know that there's proximity plays a role to fire and heat. And if you knew that the Earth's orbit was actually elliptical about the sun and not circular, then you could kind of put two and two together, and that would be a very logical assumption. But a couple of things. The first one is that the Earth's orbit is just barely elliptical. It's almost a circular orbit. If it was more elliptical, then maybe the time of the year, maybe that would play a much bigger role. Maybe the seasons on Earth would be dictated by that, but it isn't. The other thing is that at certain times of the year, part of the Earth has summer and part of the Earth has winter, and it flip-flops, right? So if it was a proximity to the sun thing, the whole Earth would have winter at the same time. The whole Earth would have summer at the same time. It's because of the tilt of the axis. So you can see here that I've picked a point in the northern hemisphere, but if I pick a point in the southern hemisphere, if I pick this point over here, and then we say at some later time it's over here, then this would be winter, and this would be summer, right? We would say it's flux. It's a flux thing. Flux is the amount of something penetrating a surface area. And we deal a lot with flux in physics 4b. Electric field lines penetrating a surface, magnetic field lines penetrating a surface. This would be the sun, how the sun's light is concentrated on the surface. And the angle makes a big difference with flux. Okay, so now you know why we have seasons on it. You probably already knew, but that's okay. Okay, so I thought that kind of falls in. We were talking about tides and what causes tides, the fact that we have a different force on one side of the Earth due to the gravitational attraction with the moon or with the sun, both contribute to our tides, than we do on the other side. Because the Earth is so big, the gravitational force on one side is bigger than the other side. So when the Earth gets pulled, one side gets pulled a little harder, it tries to elongate. Well, the Earth is pretty rigid. It can't elongate very much, but the oceans can, and they do. They elongate, they bulge out a little bit. And as the Earth rotates underneath that ocean, then we can see the tides going in and out, up and down, as the Earth rotates under that. All right. Let's see, there are a few things I wanted to, let's go back and kind of do a little review and watch a couple of videos before we move into new material. Let's watch this one first. Here I have an ordinary push broom. I'm going to find the center of mass by sliding my fingers together along the handle. They end up at the balance point, the center of mass of the broom. The question is, if I cut the handle at that location, which side is heavier? The broom side or the handle side? Pause the video and make a prediction. Okay, we've got the broom balanced at the center of mass. If we cut the handle there, which side is heavier? Sure, you want them to, you're going to predict they have the same mass? That's okay. Let's watch. I'm an experimentalist. Let's see what happens. I probably could have gone a little faster through this, but it builds the suspense. Now, let's see how much each side weighs. First, we'll hook up the handle to our spring scale, and it's about 2 newtons. Now we'll hook up the brush end to the spring scale. And it's about 4 newtons. The center of mass of the object is the balance point. What does that mean? It means the net torque is 0. The torque cancels out. The brush end is fairly close to the balance point. So there's a lot of weight there, right? But it's all really close to the balance point. So in order to produce the same amount of torque as the weight way out at the end of that handle, it has that huge lever arm, you need a lot more weight on the short side. But the handle end protrudes way out from the balance point. Okay. Why does that trick work? I can hold the stick on my fingers and slide them together and I end up at the center of mass. Slide my fingers together. One finger sliding more than the other, then the other one slides, then this one. And where do I always end up? At the center of mass. Here's my rod, right? And I've got my fingers here and I'm moving them in. Well, which one is going to slide? The one that has the least friction. Friction is determined by the normal force. So if one is too far out, it will have a bigger normal force. And so it will have a smaller normal force. And so it will slide in, right? Because it's a torque thing. So if one of my fingers ends up over here, this has to provide a really big normal force. This one would provide a small normal force to keep the system for the torque to be balanced. Thank you. There we go. Thank you. I'm going to be switching back and forth a lot today, so that'll probably happen again. Okay, here's my broomstick, whatever. My fingers down here. If one finger is closer to the center and the torque is balanced, that means that this has to be providing a much bigger normal force than this one for it to produce the same torque. So if the normal force is bigger, the friction force is bigger. So this finger is going to slide in a little bit. And if this one gets too close, if this one gets over here, then its normal force is going to be bigger. And this one will slide in a little bit. So you can see how this trick with your fingers always works, because the net torque has to be zero. So as whichever finger is closer to the pivot point, to the center of mass, whichever finger is closer has to produce a bigger normal force, and it's going to have more friction on it, and the other finger will slide first. Okay. Let's see. I had oh, this one. Let's do this one. We need to see this clip from The Simpsons to straighten this out on angular momentum conservation. Let's see if they get it right.
Run, Ralph, run!
Okay.
Time to do what I've never done as principal. Something.
Skinner's spazzing out!
I'm not spazzing out. I'm using the principle of conservation of angular momentum to turn the container.
That is so cool! That's the kind of stuff they should teach in school!
Okay, one more time.
To turn the container.
They get it right. He's standing on top of the container. He's running one way, and the container is spinning the other way. Conservation of angular momentum. They got their physics right.
That is so cool! That's the kind of stuff they should teach in school!
Okay. All right, let's do, let's see, should we do the, let's do another video while I've got it here. Let's do the bullet block.
All right, here is the setup. I have a rifle mounted vertically, and we're gonna shoot a bullet into this block, right into the middle of it. And so obviously the block is gonna go flying into the air. But we're gonna do this again, and instead of firing the bullet right into the middle of the block, we're gonna shoot it off to one side. And I want you to make a prediction. Will that spinning block, when we hit it to one side, will it go the same height as this first block? Will it go not as high, or will it go higher?
Okay, so versus being shot in the middle when you shoot on the side is the question, right? Like,
Yeah, how high will it go in comparison?
You understand what he's doing here, right? got two blocks. One, the bullet strikes right at the center of mass, and the block goes straight up and ends up here. And the second one, the bullet strikes here. So as the block comes up, it's going to spin, right? Question is, does it make it as high as the first one? Same height, higher, lower? Think about it for a second. Let's see what the experts say.
It depends on if the bullet stays in the block. And I'm assuming it does?
It does stay in the block, yeah. I guarantee you that.
Same height. I'm purely basing it on just like an instinct that I have.
I feel like I'm being tricked.
I just feel like you're trying to trick us and that it's going to do something that we can't predict.
I thought the obvious answer is not as high, so I'm going to say higher.
I'll say higher. Finally off the camera. But it's going to like fly in a different direction or something. So you have angular momentum, which is L, and you have translational momentum, which is P.
Yeah.
When you hit it in the middle of the block doesn't really spin at all, so it just goes up to a certain height. But when you hit it on the side of the block, it's going to be spinning, so it's going to have imparted some kinetic energy, so there won't be as much potential energy.
And so the total energy of the system
basically has to stay constant, and the kinetic plus potential, which would be the height it goes to, will have to be constant. So if it's spinning and has kinetic energy, it can't go as high. That's my prediction.
So my prediction is it'll go up, not as high, but it'll spin more if it's hit to the side. Am I wrong?
I want you to think, which do you think is the most reasonable, and then click one of the annotations above. All right, are you ready? Make your prediction in 3, 2, 1.
Okay. I don't know if you're familiar with this. It's really good. He does really good videos. Check it out. Excuse me. Okay, so let's see what happens.
All right, let's watch it. Hopefully I'm not horribly wrong. Derek's giggling to himself right now.
Okay, you have made your prediction. Now it's time to find out which block went higher, the one that's shot off center or the one that shot right into the center of mass. Okay, we're just getting set for shooting straight into the block. How you feeling about this one, Dave?
I think this is the one, I really do.
Okay, range is going hot in 3, 2, 1.
We've moved this block, so now the gun is actually firing into the right side of the block. So presumably, one imagines that the block will spin anti-clockwise.
3, 2, 1.
Now check out the high speed.
Okay, there are no sideways forces, right? The only force is straight up. The block had to go straight up. It's not going to go flying off to the side, right?
Speed footage. You can clearly see that both blocks go to the exact same height, even though one is rotating. And that's a bit strange because they were both hit by the same type of bullet from the same rifle, so presumably it had the same kinetic energy. And they both go the same height, so they both have the same gravitational potential energy, but one is rotating. And so it has that additional rotational energy. So one block has more energy than the other block.
I don't know if I buy that, Dr. Muller.
Yeah, talk to me.
Yeah, I mean, so you're telling me you just created energy?
Not necessarily created energy.
Okay.
So
What's the other option?
what are you thinking there?
I am potentially surprised.
Is it the same height?
Speed footage.
Obviously I'm wrong.
They went up to the same height, which is incredibly confusing to me.
Why is that confusing?
Because where's that extra energy coming from?
But the fact is that one block clearly does have more energy. You think about them both at the top. One's spinning, one's not. They basically have identical gravitational energy, but one does have additional rotational energy. How is that possible, and why is it happening?
No, explain it to me.
I don't want to give you the answer right away.
I love it when you say that. I don't want to give you the answer. That means you don't know. I love that.
So if you can make me a video response, I would love that. Or if you just want to post your idea in the comments below, that'd be great. And I will reveal the correct answer next week. So subscribe to the channel if you haven't already, and you'll find out in a week's time.
After I have time to pour over the footage and consult a very smart man in the subject. that's what you get to say.
Okay, a lot of people thinking about energy on this one. But what should we have been thinking about?
In my last video,
momentum. We should have been thinking about momentum. That's exactly right. So lots of energy was lost when that bullet went into the block, penetrated into it, left a hole there. The bullet probably even melted because of the heat that was lost. And in one case, obviously a little less energy was lost than in the other case, but in both cases, lots and lots of the initial energy of the bullet was lost to heat and deformation and other things. When I say lost, I mean transformed into other types of energy that is non-mechanical energy.
We performed an experiment in which two identical wood blocks were shot with the same rifle, one through the center of mass and the other one slightly off to one side. Now if you haven't seen that video yet, then click here now and go and watch it. Or if you're on a mobile device, click the link in the description. So the question was, compared to the block shot straight through its center, how high would the block shot to one side go? Now 60% of you predicted that it wouldn't go as high.
Didn't seem as high.
Now check out the high speed footage.
Oh no.
You can clearly see that both blocks go to the exact same height.
Oh, come on.
19% said that it would go higher, and only 21% correctly predicted that both blocks would go to the exact same height. So most of us got it wrong the first time around, and that includes Henry and me and Destin, who has a lot of experience with this stuff.
I mean, I can't tell you how many times I've hit wood with a rifle.
So even experienced and intelligent people get it wrong sometimes. In this case, I think the result was particularly counterintuitive because the spinning block clearly ended up with more energy than the other block. So I asked you guys to make me a video response and explain what is happening, and this is what I received.
If you imagine the bullet traveling through the center of the block, then after the collision, the bullet is
Whoa! That is a lot of video responses, and that's not even all of them. I've got to say, I was blown away by all of the great video responses I received. You guys are awesome, and I really, really appreciate all the effort you went to. You know, some of you actually replicated the experiment, perhaps with different setups. The experiment was featured on blog posts including Scientific American and Wired. There's an interactive simulation you can try, link is in the description, and someone even made a webcomic. It is so incredible, you know, watching all of those video responses, and I did watch all of them. That was my proudest moment making this YouTube channel. Seeing all of you guys doing science and getting so involved and putting in so much effort, It just blows my mind. It's amazing. Thank you guys so much. Thank you, thank you. I can't even put it into words how awesome it is. Woo! So what is the answer? How could two identical blocks shot with the same rifle end up with different amounts of energy? Well, some of you felt that the amount of rotational energy would be basically insignificant.
What if the amount of energy necessary to get that very small block rotating really is negligible in comparison to the amount of energy necessary to lift it into the air and resist gravity?
Well, we can calculate it because the spinning block was rotating at about 11 times per second. So you can calculate that its rotational energy would be equal to 50% of the gravitational potential energy when those blocks were at their peak. So the spinning block actually had 1.5 times the energy of the non-rotating block. And in my books, that is not negligible. So what else could be causing this? Well, some of you actually measured the height difference using pixel counters and found that the blocks didn't go to exactly the same height. So this raises an important question, which is how different would those heights have to be before you can think that there really is a difference there? Well, given that the rotational energy is about 50% of the gravitational potential energy, you might expect the spinning block to go half as high. But looking at the video footage, you can clearly see it doesn't go half as high. It goes basically to the same height. To know for sure, you'd probably want to do the experiment a number of times. In science, you got to repeat things and make sure what you saw is not just a fluke, that it will happen every time. So in fact, we did repeat the experiment a number of times, and here are all of the blocks lined up side by side so you can compare their heights. The blocks clearly do not all go to the same height. So you might say, Derek, you were tricking us. You just picked the two that went the closest and used those. It's true, I did do that. But the point is, do the spinning blocks go systematically to a lower height than the non-spinning blocks? And I think from the video footage, the answer is clearly no. So why not? Well, another common response I saw was that air resistance must play a role, that the spinning block exposes a smaller surface area as it's traveling upwards, and this means there's less air resistance impeding it, so even with a lower velocity, it could make it to the same height as the non-spinning block. But you can do the calculation and find that the difference in air resistance would be at most about 0.6% of the weight of the block. In other words, negligible. So what is the real answer? Well, there are a number of ways of approaching the problem, and I saw you guys try almost all of them: force, torque, momentum, energy. But the easiest one of these is the law of conservation of momentum. You see, when the bullet is fired out of the rifle, it has a certain amount of momentum entirely in the vertical direction. And when the bullet becomes lodged in the block, the bullet and block together must have that same momentum that the bullet had. Now, it doesn't matter where on the block the bullet hits. Because the bullet had a certain momentum before it hit the block and bullet together afterwards must have that amount of momentum upwards. So this means, regardless of whether the block is spinning or not, it must have the same upwards velocity so that it has the same momentum. So it will go to the same height regardless of whether it's spinning or not. It is simple conservation of momentum. Momentum is always, always conserved. It is something you can always rely on, and it's why you should think about it first. But some of you may say, okay, well, there's also angular momentum in the spinning block. But the point is, angular momentum and linear momentum are independent, and they're conserved independently. So you can simply think about the upward momentum of the bullet, and that's going to have to be the upward momentum of those two blocks, and it doesn't matter that one's spinning because they have the same total linear momentum upwards, so they have to go to the same height. But if that is the case, why does the spinning block end up with this extra rotational energy? Well, the thing about energy is it's a little bit tricky. Although total energy is conserved, the energy of motion, which is called kinetic energy, is not conserved. So what happens is, as the bullet strikes the wood, a lot of its kinetic energy is lost, heating up the wood, creating sound, and deforming that wood block. So it would be possible for the rotating block to end up with more energy of motion, more kinetic energy, if the bullet loses less energy, deforming the wood and heating it up and creating that sound. And this kind of makes a little bit of intuitive sense, because if you imagine the bullet entering the block on the side, the block will be moving away from it faster because it's rotating. So that may mean that the bullet doesn't penetrate in as far, and so it wouldn't lose as much energy as it's entering the wood, which explains why the block has extra energy, allowing it to rotate and go the same height as the other block. Let's have a look at how far in the bullet went into each block. This is our first test. Here we go. This is the one where it went straight in.
Uh-huh. There.
Yep.
Now we come over here to the off center.
This is where the bullet went in off center.
So it's not going in near. See where my.
Yeah. Let's see the other one.
Okay. There it is, all the way in. There it is, part way in.
See you tomorrow. So the bullet didn't go as far into the spinning block.
Right.
So that was pretty convincing evidence, but just to be extra sure, we x-rayed both blocks, and this is what we saw. I'm going to overlay the block so we can see the difference in penetration depth. Hang on. It looks like both bullets penetrated each block to the same depth. So does that mean our theory is wrong? Well, let's think about how different the bullet depths should be. I mean, when the bullet strikes the block, it actually loses 97% of its original kinetic energy. And the amount of rotational energy the spinning block has only works out to about 1% of the original kinetic energy of the bullet. So we would only expect a difference in depths of about 1%. And for our measurements, that would be about 1/10 of a millimeter. That would be immeasurable. And that is what we see. So, although this answer is a little bit unsatisfying, at least it is the truth. As an extra challenge, I want you guys to think about how we could perhaps modify this experiment so the difference in bullet depth would be measurable. You can leave your answer in the comments or make me another video response because I love those so much.
Okay, if you're not familiar with his channel, check it out. That was a good recap of linear and angular momentum. All right, we ready for some new material? Come back, come back. The correct answer is yes. Ah, it didn't like that, did it? Okay, third time's a charm. All right, we are now doing oscillations. All right, if we make our surface frictionless, our mass will be attached to the spring, and if it's sitting at the equilibrium position of the spring, there's no force on it right there. If we pull the mass out a little bit, then the spring becomes stretched and it pulls the mass in the opposite direction. If we're careful with our signs, the force from the spring minus kx, right? What is going on today? Maybe Okay, let me try closing some windows here. Yes. Negative, because it's in the opposite direction as the displacement, x. So if x is in one direction, the spring force is in the other direction. And then we say sum of the forces equals ma. So if the force is minus kx, and what is a? It's the second derivative of the position. With respect to time. And these are functions of time. X is a function of time here, right? I should really write it. So what we're saying here is, I'll do it one more time here. Minus k over m times x, right? Is that more clear? X is a function of time, right? It's if we let go of this mass, if we stretch the spring a little bit, let go of the mass, what's it going to do? It's going to go back and forth and oscillate forever, right? So the position is some function of time. The equation here is telling us that if we take two derivatives of that function, we're getting negative a constant times the exact same function. What function can we take two derivatives of it and we get negative a constant times the exact same function? Any cosine or sine function, right? So if that's our position as a function of time, and we take a derivative of that, we get negative omega times a times the sine of omega t plus phi. And what is that? That's our velocity. And if we take a second derivative, what do we get? We get minus omega squared, a cosine. That's our acceleration. What is this? That's our position as a function of time. That's x. So this thing here must be minus k over m, right? This x times negative k over m. Take two derivatives, we have to get x times negative k over m. So omega squared is equal to k, or omega, I'll just say omega. Omega equals the square root of k over m. What is k? Is the spring constant. And m is the mass that's moving back and forth on that spring. So this satisfies this differential equation here. We get this differential equation, and this differential equation is relatively easy to solve, right? Take two derivatives, you get negative a constant times the same function. So we call this simple harmonic motion because it's this is an easy one for us to solve. Okay, what else do we have? We got a spring constant, we've got a mass. What is omega? Omega is our angular frequency. And it has units of radians per second. It's a lot like angular velocity. We use omega for angular velocity. We use omega for angular frequency. Has the same units. It's very similar. The reason we don't call it velocity here, angular velocity, is because, where's my mass in the spring? Nothing is moving in a circle, right? The mass is not moving in a circle. It's not moving with some angular speed, right? It's oscillating back and forth, and it completes a cycle. We stretch it out and let go. It gets pulled in, goes through the equilibrium position of the spring, goes in until the spring is compressed, gets pushed back out through the equilibrium position of the spring, back out to its maximum displacement. And that's one complete cycle. And then it does it again, completes another cycle. And so the number of cycles that it completes in a given amount of time is the frequency of the oscillating motion. Anytime you have repetitive motion, we have certain terms we use. Frequency, period, those are two that we talk about a lot. The frequency, F, is the number of cycles per second. Where are we here? Frequency. And F has units of cycles per second. Cycles, of course, is not a unit. So it's just inverse seconds. And we get tired of writing 1/seconds, so we use hertz. Hertz is an inverse second. Okay, oops. And there's a link between these two. Omega is equal to 2 pi radians per cycle times the frequency, the number of cycles per second. So I always like to think, of course, we know radians is a unitless quantity. Really, omega has units of 1/seconds, but I always like to think radians per second. It just helps me keep track of things, and I end up, it keeps things straight for me when I think radians per second. And of course, cycles is not a unit either. It's really has units, frequency has units of 1/seconds, inverse seconds. But if I think cycles per second, it helps me keep track of things. And when I link the two, how do I get from cycles per second to radians per second? I multiply it by 2 pi radians per cycle. Why do I do that? So let's take a look at this situation. We've got something oscillating back and forth and back and forth, and it's doing repetitive motion. Repetitive motion. Well, what repeats? What motion repeats? Same over again? Something moving in a circle, right? Something moving in a circle. If I have an object, a wheel here spinning, and there's a peg sticking out of the wheel there, at some instant in time, the peg is right there moving with speed v, and at some later time, it's over here moving, right? And if I wait long enough, where is it again? It's right back at the top, moving with speed v again. And if I wait the right amount of time, boom, there it is at the top again, moving with speed v. So this is cyclical motion. This is repetitive motion. Something moving in a circular path is a cyclical process, repetitive, over and over and over. We get the same thing. And that's what I get with a mass on a spring. I get the same thing over and over and over again. So I should be able to link these two and think about it in terms of sort of circular quantities, things like sines and cosines, things like omega, which tells me this angular frequency, turning things into these angular quantities. Even though the mass is moving in a straight line back and forth on this spring, I can think about it as something moving in a circle because it's this repetitive process. Okay, let's take a 10-minute break and we'll talk a little bit more about how we use the circle and other properties of repetitive motion. All right, so we have something that we are describing as circular motion, but it's not circular motion, it's just repetitive motion. How do you not confuse the two omegas? That's a good question. Basically context, right? Just like, you know, when you learn to speak a language, we've got, how many different twos do we have, right? We've got two, right? They all sound the same, but when you're talking with someone, you know which one they're using because of the context, right? Or words that are spelled the same but have different meanings, but from the context you have to be able to figure it out. They're actually very similar because what is the angular frequency? The angular frequency is the speed something would, the angular velocity something would have if it was moving in a circle. So let's take a look at this situation again. I've got my disc here with a peg sticking out of it, right? And it's rotating. And I'm going to put some lights up here at the top and shine the light straight down. So we've got light coming straight down from the top. This is a vertical, the disc is vertical, and there's a peg sticking out, and it's going around like this, and light is coming down. And I'm going to look down here at the shadow. Down here on my tabletop, I have a mass attached to a spring. And where's the shadow from that peg? It's right on top of the box right there. That's the shadow is right there. And there's my peg. Okay, there's a peg sticking out, light's coming down. The shadow is right below it, okay? Now, I stretch the mass and I let go, and the mass is gonna oscillate back and forth and back and forth and back and forth. And it comes all the way into here. So this is x equals 0. This is minus a. And it comes all the way out to here. As this thing rotates, where does the peg eventually end up? Eventually, the peg, I'm going to use a different color. I'll use green. Eventually, it ends up over here. And where's the box end up? Here. And where's the shadow? Right there. And then at some later time, it's over here. And the shadow is there again, but the box is moving in the opposite direction. And at some later time, it's over here. And the mass is here. And where's the shadow? Right there, right? So you see what's happening. The circle is moving, the peg is moving in a circular path. And the box is matching it. So When the peg is moving in one direction with maximum speed, the box is moving in the same direction with maximum speed. When the peg gets to the edge, what's it doing? It's not moving left and right at all. It's only moving vertically. So the box comes to rest momentarily at that instant, and then they boom, move back together, and they have maximum speed in this direction when the peg is at the bottom. And then the peg gets to a point where it's not moving horizontally at all. It's only moving vertically. So the block is momentarily at rest there. And they follow each other around like that, right? So you can kind of see how this circular motion matches the repetitive motion of the block on the spring. What's the angular speed of this wheel? Omega. It's the same as that angular frequency of the mass on the spring. So they're related, I guess. All right, so let's take a look at what's going on at the different cycles, because we can do all of this already. We know about masses on springs and things. Let's just take a quick look here. We've got at this situation, this is our starting point. We're going to stretch the spring a little bit and then let go. We're going to release the mass here. This is our starting point. This is t = 0. So what do we have? X, V, A. Am I going to run out of room here? I'll just go a little bit bigger. X, V, and we've got kinetic energy, and we've got U spring. Okay, there we go. And we'll walk our way through a whole cycle. All right, can you fill in the rest of these columns? What's the position? A. What's the velocity? 0. If the velocity is 0, what's the kinetic energy? Zero. What's the spring potential energy? 1/2 k x squared, right? X is A. 1/2 k a squared. And what's our acceleration? This is the point where we have our maximum acceleration. What's causing the acceleration? What's the only force acting on our object in the horizontal direction? The spring, right? Yeah. So F = ma. Acceleration is going to be kx/m. So in this case, it is, this is the magnitude, right? So in this case, it's going to be minus K over MA, or we could say minus omega squared A. Because omega is K over M. And we know it's in the negative direction, right? The acceleration is in this direction. The acceleration is in that direction. The force is pulling it that way. If we let go of it, where's it going to go? It's going to go to the left. Okay, we good with that? And then we wait a little bit, and where is that mass? It's moving through x equals 0. With some velocity in that direction, right? Can you fill in this row? What's the x position? I'll do the easy one for you. If x is 0, what's the acceleration? Zero, right? The spring is not stretched or compressed at that minute, at that instant. So there's no force on this thing. The speed is maximum, but the acceleration is 0 at that point. And what's the spring potential energy? Let's start with the easy ones, right? If x is 0, if that spring is not stretched or compressed, it can't have any energy stored in it. So all of the energy of the spring, where is it now? Yeah, it's all in kinetic energy. It's just going back and forth. Kinetic energy, potential energy. Kinetic, potential. At some point in between, some point between t equals 0 and this time, we have both kinetic and potential, right? But I'm only picking the points where it's all switched to kinetic, potential. I'm not picking the ones in between. What do we call this time? It is how much of the whole cycle? One quarter. Yeah, we are 1/4 of the way through the whole cycle. So the time it takes to complete a whole cycle is called the period. We use a capital T for period. Did I write that somewhere? Let's add that up here. Let's go back and add that. Capital T is the period. That's the time one cycle. So its units are seconds. And I'm going to squeeze one more little thing in here. If the period is the time to complete one cycle, and the frequency is the number of cycles per time, that means they are inverses of one another. The period is equal to 1 over the frequency, or vice versa. Okay. Now, what is V? This is our maximum velocity. How do we find that? Well, a couple of ways we can do that. The easiest is probably use energy conservation, right? We know that 1/2 mv squared has to equal 1/2 ka squared when the velocity is at its maximum value. So what do we get? We get the V maximum is equal to the square root of k over m times the amplitude. And what is the square root of k over m? It is omega. So we can put over here omega a. But it's going in what direction? It's going in the negative direction there. That's one way of finding the maximum velocity. What's another way of finding the maximum velocity? Using our equations. Where's our equation? Oh, right here. This is the equation that we get for velocity. What sine, the most it can be is 1 and -1, right? It oscillates between 1 and -1. So this tells us our maximum value right here. Omega A is the maximum velocity. It's either going to be positive or negative, in the positive direction or the negative direction. In this case, we have our maximum velocity, but in the negative direction, omega A. So far, so good? I'm going to erase this and we will continue. With our cycle. We'll finish it off a little quicker here. So at some later time, our box is here. V equals 0 again. We are at the halfway point through our cycle, halfway. X is now at -a. Our velocity is 0 again. If our velocity is 0, our kinetic energy is 0. Our spring potential energy must be 1/2 ka squared. And our acceleration is maximum. It's k over m a, or omega squared a, and it's positive now. Acceleration is to the right. And a little bit later, where's our object? We are at, where are we? 3/4 of the way through our cycle. It's back at x equals 0. If x is 0, acceleration and spring potential energies have to be 0. Our kinetic energy is 1/2 ka squared. And we're moving with our maximum velocity in the positive direction. And then we're back at our starting point. V is 0 again. And I want to draw one more in between. So this is, we've completed our cycle. We're back. Everything here should match what we have in the first row. But let's pick a point in between. Let's say we are here. and it's moving in this direction. This is just going to be any time t. We don't know exactly what the time is here. Some position x. It's moving with minus v. Instead of minus omega squared a, we just put an x in, right? A is not equal to, sorry, x is not equal to a anymore. It's any arbitrary point in between. This is our 1/2 mv squared and our 1/2 k x squared. We don't know exactly what those are. We'd have to be given a little more information to figure all that out. But there's some mix, right? It's a mix of kinetic energy and spring potential energy. It's not all one or the other when we're in between like that. Okay, let me do a quick summary and then we'll do this worksheet. We call this simple harmonic motion. Because it's simple to solve this differential equation we get. And so what did we use? We said any sine or cosine function, right? That we could use to describe the position as a function of time. X is a function of time. Some A amplitude, cosine, omega t plus phi. What is A? A is the amplitude. That's the maximum displacement. Cosine can only be as big as 1 or as small as -1, right? A cosine varies between 1 and -1. What if I stretched my spring by 2 meters? Well, that's what that A is for out here. That is the multiplier that tells me my maximum displacement, the amplitude. Omega, we already said, is the angular frequency. And that's equal to 2 pi f, and it's radians per second are the units there. F is our frequency. That's the number of cycles per second. Units are inverse seconds or hertz. T is the period. That's the number of seconds per cycle. So the units are just seconds. And of course, we have this relationship with T and our frequency. Okay, there's one thing I haven't talked about yet. This phase angle. What is it used for? To set the initial conditions. Because I said any sine or cosine would work to satisfy our differential equation. And what did I then what did I do? I wrote out a cosine function here. I could have just as easily written out a sine function. But if I pick cosine and you pick sine, we have to be able to explain it the same way. We have to get the same answer, right? They both should work. Well, that's what this is for. Because a sine plus 90 degrees or minus 90 degrees or 180 degrees becomes a cosine, right? I can just shift it by pi over 2 one way or the other and turn a sine function into a cosine function. So that's what this is for. If my initial condition, let's just talk about it for a second. If my initial condition is this, okay, let's find our phase angle. If this is our initial condition, what would our phase angle be? What happened to my function here? I hate when it does that. Equals A. At t equals 0, we want our x to be plus a. So we want our cosine to be 1, which means we want whatever's in the parentheses here to be 0. So if t is 0, that takes care of that part. We have to set phi equal to 0 to keep this at x equals a. Did you follow that? Okay. What if at t equals 0, our box was moving in this direction? So we say 0 is equal to a cosine omega times 0 plus phi. So the cosine of phi has to be 0. So that means what does that mean? That means pi over 2 or 3 pi over 2, right? We don't know which one. We need more information. Well, we have the information. it's moving to the left. The velocity has to be negative. Both give x equals 0 at t equals 0. But only one will give v So in this case, I said it was moving to the left. The velocity had to be negative. I could have said it was moving to the right at t equals 0. Well, one of these would give moving to the left at t equals 0. The other one would be moving to the right. So we have to get the right one. We have to look at the velocity now. What is the velocity? It's minus omega a. Where is our velocity function? Whoa, right here. Velocity is minus omega a sine. So I go back down here and I say the velocity is minus omega a sine omega t plus phi, and this must be negative. Right, this is at t equals 0. And so we're going to put in pi over 2 or 3 pi over 2. This must be positive. So which one gives us a positive? Pi over 2. Okay, we'll do that a little bit more. But that's what that's for. It's to change. I told you any sine or cosine would work. So that means that both sines and cosines have to work. That's what that's for. It's for adjusting it shifts the whole sine wave, right? It shifts it one way or the other to match the initial conditions of the problem. All right, let's do this. A cart is attached to a spring, displaced from equilibrium, and then released. There's no friction. We're looking at a graph of velocity versus time for the cart. Positive is to the right. They've indicated our coordinate system here. Positive to the right, negative to the left. Okay, first question. What's the period? Okay, we're looking for the time it takes to complete one cycle. I always like to look for a maximum or a minimum. So if I look for a maximum, I have a maximum here, I have a maximum here, and that's completes one cycle. So the time it takes to complete that cycle is 8 seconds. If you look for zeros, you have to be careful. You could say, oh, I have a 0 here and I have a 0 here. But those are not, that's not one cycle. Here, you're at 0 and it's going positive. Here you're at 0 and it's going negative. Those are two different places. You have to pick identical points to get a full cycle. So 0 going positive, 0 going positive. I'll get rid of this one in the middle. And then this could be one cycle also. But be careful if you're using zeros, be careful, make sure it's the same 0. 0 going positive both times, or they have to be identical. So picking a maximum is maybe easier to spot. But in this case, what is it? It goes from 2 to 10, that's 8 seconds. What's the frequency? One over 8. In which direction was the cart displaced from equilibrium before it was released? In which direction was the cart displaced from equilibrium before it was released? Which direction did we displace this thing before they released it? Here, you got a cart sitting here like this, right? We could have pulled it out this way a little bit and let go. Or we could have pushed it in this way a little bit and let go. Which one did we do? To the right or to the left? There we go. Because we have a chart here that shows us velocity versus time. And as soon as we let go, what does the thing do? It starts moving in the positive direction. It starts moving with positive velocity. If it moves in the positive direction, we must have pushed this cart to the left. We must have pushed it in the negative direction. Okay. All right, let's if x is a cosine omega t plus phi, Find A, omega, and phi. This is the questions on C here. What direction was the cart displaced? Right, so we know that it says here the cart is displaced from equilibrium and released. We want to know, is it pulled this way and released? Or is it pushed in this way and released? And we look at our chart here, our graph, and our graph is showing velocity versus time. When did we release it? At t equals 0, right here, right? And as soon as we let go of it, what did the cart do? It moved with positive velocity, and then it moved to the bigger positive velocity, and then a bigger positive velocity. Well, positive velocity is to the right. So the only way the cart could have moved to the right is if we initially pushed it to the left. We displaced it to the left. Okay, so you're figuring everything out? We're looking at velocity versus time. So, as has been pointed out here, this is what we're looking at, right? Do we get omega yet? Or A? So we found the frequency earlier, right? F was we found earlier. And we know omega is equal to 2 pi times the frequency. So we should be able to get omega right away. Okay, what's next? What's the amplitude? Right, so let's take a look at this. We are looking here at velocity versus time. Velocity versus time. And the maximum we get here, the maximum is 4 centimeters per second. But that's the maximum of velocity. That's the amplitude of the velocity versus time function, right? That's this value right here. The sine function, the maximum the sine function can be as 1. When the sine function is 1, we get our maximum velocity. In this case, it's 4 centimeters per second. So we can set that equal to our maximum. And that has to equal 4. So we end up with our amplitude is 16 over pi, and that would be in centimeters, right? Okay. How about our phase angle? Right, we know that it was displaced to the left in the negative direction. So at x equals 0, we're at negative a. So negative a has to equal a cosine omega times 0 plus phi minus 1 has to equal cosine phi. So we get pi. Let's just make sure that works with our velocity. If we check our velocity at t equals 0, we've got 0, right? It's released from rest. Question about the initial amplitude. We know that it either starts out here at A, or it starts over here at minus A, right? It's because it's released, it's displaced from equilibrium and released. And at t equals 0, it's not moving, right? It's released from its maximum displacement. And it immediately starts to move in the positive direction. So it has to be on this side. If it immediately goes in the positive direction, that's what we said over here. It had to be displaced in that direction. And so we plug in V is 0. So we get 0 is minus omega A sine of omega times 0 plus phi. So we get sine phi has to be 0, which means 0 or pi, and pi works, right? We got a pi here. Oops. So we can use pi. We want to pick the one that matches. We're good. Okay. We can do a little bit more of these next time, tomorrow. All right, I'll stop the recording. I'll stick around and answer questions. Otherwise, we've got our normal office hour at 4 o'clock, and there will not be a review tomorrow. No review Friday afternoon. We'll just have our normal class. And then I'll send out an email with when I'll have reviews and things before the final. We'll have extra office hours and reviews next week.